Great. Well, first, just a shout out to all the participants who've made it through really a remarkable week of science, fact, theory, some speculation. Now we'll get into some serious speculation with the coming session. And also just a shout out to Elise, Dawn, Ellen, the entire team for putting on such a remarkable meeting. So until 25 years ago, exoplanets was the realm of theorists, philosophers, and movie producers. But the revolution in exoplanet science that started in around 1995 has produced remarkable new insights, but still leaves a lot of unanswered questions. We still don't know if planetary systems with the same configuration as our own is unique or not. What is the occurrence rate of habitable rocky planets? Are there other habitable worlds? Is there life on these other habitable worlds? Fortunately, what we do is capture the imagination of our scientific colleagues, and more importantly, the taxpaying public. And the revolution will continue with some new telescopes that will actually address the sort of questions that remain unanswered. So we have a panel of people who are deeply involved with these different initiatives, and I'm pleased to sign off and let each of them take about 12 minutes. I'll time you with Ellen's help. And we'll start off, I guess, with Christine talking about the most imminent of those, JWST. So, Christine.
Can you see my screen?
Yes.
Good. Maybe go to full screen. Yeah, there we go.
Okay. Oh no, I had a script here, which I have now just lost. Okay, well, I'm gonna try and wing it because I can't access my script. So hi, my name is Christine Chen, and I'm the JWST Science Policies Group Lead at Space Telescope. Yes, I'm here to tell you about JWST Cycle 1 exoplanet and disk observations. And I just wanted to say that this presentation is really meant to be illustrative of the capabilities and not really an exhaustive presentation. So just to give you an idea of all of the things. Oh dear, this is the wrong one. Sorry. I apologize. Shoot. I thought I had the right slide deck up. This is embarrassing. I'm so sorry. All right. Sorry about that. Okay, so this is really meant to be illustrative of the programs that JWST will complete and is not meant to be exhaustive of everything that it will do in Cycle 1. So I have a much longer pre-recorded talk, but today I'm just really going to focus on the things that are shown in the darker color. So these are the Cycle 1 observing programs that are related to protoplanetary and debris disks, particularly characterizing dust and gas, searching for exoplanets and disks, and characterizing the surfaces and atmospheres of exoplanets. If you're interested in the other material, I refer you to the much longer recorded presentation. So just diving right in, the JWST Cycle 1 program is really going to build on observations that have been made during the past 10, 20 years using Spitzer and also ALMA. So just to show you some examples of characterizing circumstellar matter in disks, there are a number of programs on protoplanetary disks. This nice spectrum that was obtained with the Spitzer IRS gives you a feeling for some of the materials that were seen in protoplanetary disks. These happen to be absorption features. You can see features due to water ice, methanol ice, silicates, and carbon dioxide. So one of the great revolutions of JWST is the increase in angular resolution compared with Spitzer, going from an 85-centimeter telescope to a 6.5-meter telescope. And so really, JWST will enable mapping the locations of these materials as a function of position, whether that's scale height or radius in the disk. And so I've cited here a couple of programs that are particularly interested in these issues of volatile ices and protoplanetary disks. One happens to be an early release science program, and then the other one is a cycle 1 program that was selected by the time allocation committee. So moving on, JWST will also build on Spitzer observations of volatile gases in protoplanetary disks. So probing gases that have temperatures of maybe 500 to 1,000 Kelvin that have been seen again in Spitzer IRS spectra. And since that time, we've also learned a lot about the geometry of the dust in these disks from these very high angular resolution observations by ALMA. And so the observations will enable us to create inventories of major molecular species to help, for example, understand dispersal processes. And you have a feeling for what the expected kind of richness of the spectrum is. At the bottom, there's a simulated Miri MRS spectrum of water emission from Colette Salek. So JWST will also enable observations of debris disks. So now these are disks that are not protoplanetary, that have much less gas in them, as was already discussed, and the dust that's seen is created through collisions among planetary embryos, planetesimals, dust grains. And traditionally, high resolution scattered light imaging has revealed quite a lot of information about, for example, asymmetries in the disks that indicate the presence of planets, extended halos of small dust grains that are blown out of the system by radiation pressure. And these measurements also measure what's called the scattering phase function. And so this is the amount of light that's scattered by the dust grain as a function of how much that dust grain deflects the light. And so this is an example of a program that is actually a guaranteed time program. And one of the stretch goals, this particular program happens to be a NIRCam imaging program, will be to use the NIRCam medium band filters. NIRCam has a large suite of filters, but these filters could potentially enable imaging in and out of water ice and CO2 frost solid state features. To understand the spatial distribution of volatiles of disks. In addition, there's spectroscopy that will happen at mid-infrared wavelengths, as was alluded to a little bit. And this is a particular program that I'm illustrating here. This is mid-infrared spectroscopy of Beta Pictoris. There is evidence from ground-based 10-micron spectroscopy that the silicate features in this disk change as a function of position, with like the more crystalline material located at the position of the star and bands of small dust grains. And so these observations, although they're taken with Subaru at high angular resolution, are really limited to the 10 micron band window. And so again, one of the nice things about JWST is now being able to do experiments like this using a 6.5-meter mirror in space to look at the silicate emission features at longer wavelengths and understand how they change as a function of position. There were a number of proposals exploring the presence of planets and the connection of planets and disks in these systems. So this is a very nice plot sort of showing what the current phase space of our knowledge of planets is right now, with mass on the y-axis and separation on the x-axis. And you can see that there's an area that's been circled here to highlight the region that JWST will enable observations of. So particularly the detection of Saturn and Neptune analogs at wide separations. And so there are a number of programs that are focused on trying to see the planets that might be sculpting both debris disks and protoplanetary disks. So we've already heard so far this very nice story about Beta Pic and how very high angular resolution images of Beta Pic led to the discovery of structure, the inclined secondary disk with respect to the primary disk. And that led to the discovery of the Jovian mass planet in the system that has been observed for more than a decade now. During JWST cycle 1, there will be observations of 38 young stars, including famous systems such as Epsilon Eridani, AUMIC, Beta Pic, HR 8799, Kappa, and so on, to try to look for the planets that may be sculpting these systems. As already been discussed at this meeting, there has been evidence for the presence of protoplanets or planets, even in protoplanetary disks. And one thing that's been highlighted has been these observations of the Herbig AE star HD 163296. You can see the ALMA image at the top left, and to the right is a channel map with the kink that's been discussed several times. And that kink has led to the suggestion of planet in this particular system. So there are, for example, a couple of accepted GeoCycle 1 programs to investigate or try to detect the presence of this planet directly, both using the NIRCam and the MIRI coronagraphs. I wanted to give a special shout out to a couple of programs. These are what are called early release science programs. So they're being completed with director's discretionary time. And the idea is that they get executed early on in the mission to give the community an opportunity to see what JWST data looks like, particularly before the cycle 2 proposal deadline. And so the data for all these systems or all of these observations will go public immediately. One of these programs that's of, I think, particular relevance is this high contrast imaging ERS program. And it has several objectives. One of them is to, for example, begin to understand the stability and how to do PSF subtraction for JWST. And it's really important to do this starting early because JWST will have a relatively short lifetime. It's not serviceable in the same way that HST has been serviceable and able to observe for 30 years. So this program includes observations of 3 different targets, primarily using the NIRCam and MIRI coronagraphs and the nearest AMI to look at a companion near a star, and then also to look at a debris disk. And there's also some observations in there too of a wide separation companion where the contrast between the star and the companion is not so difficult to try to use, for example, the integral field units to obtain spectra of the planets there. So many of the JWST programs that are looking at giant planet atmospheres have a lot of the overarching science goals that are to measure the chemistry and thermal structure of giant planets, and in particular to measure the presence of important molecular species, and for example, the C to O ratio to constrain whether planets formed beyond the ice line and migrated inward. And there's just a large multitude of planet studies that cover a large range in phase space of mass and insulation. And so there'll be a number of issues that will be addressed, including the height and composition of the clouds, how the atmosphere varies with longitude, and how the atmosphere responds to different amounts of radiation. So the second ERS program that I wanted to highlight is one from the transiting exoplanet community. This particular technique tends to, because it doesn't rely, because it's so sensitive with the transits, essentially it can probe planets with a variety of ages. And so you'll see that this is probably the dominant way that exoplanets are going to be observed and characterized in JWST cycle 1. But statistically, they may be older objects. So many of the objectives associated with this program are the same as the high contrast imaging program, basically to try to get data into the hands of the community early to understand what the performance is and what the best practices are. And in particular with the observations, For example, there will be observations of WASP-39b, the transmission spectrum, using multiple instrument modes to try to understand what the relevant, relative merits of each mode are. And then I think the last thing I wanted to call out as far as programs go is high contrast spectroscopy. So there, unlike GPI and Sphere, there aren't modes on JWST where you can use an occulter with an IFU, but you can still do classical PSF subtraction with the IFU data to try to reveal, the spectra of companions. So the last thing I just wanted to say was, JWST is really a project for the community, and its success really depends on the engagement of the community, and that I'm really excited and looking forward to all of the things that will come out of cycle 1. Thanks.
Okay, great. Thanks, Christine. What we'll do is hold questions up until the end and let all the panelists work with each other and interact, and then take some questions also off the Q&A site. So the next facility up in the NASA suite of things is the Nancy Grace Roman telescope, which has some very interesting exoplanet prospects, and Scott Gowdy will talk to us about those. Scott.
Okay, thank you, Chaz. Everyone can hear me? Okay, so I was asked to talk about prospects for characterizing exoplanets and disks with Roman. I want to mention that a lot of this material, I got help from Ewan Douglas, Bertrand Menison, Vanessa Bailey, David Bennett, Matthew Penny, and Samson Johnson, and the rest of the Roman Galactic Exoplanet Survey Science Investigation team. In particular, the first half of the talk, where I'm covering sort of the CGI science applications. Most of the slides were stolen wholesale from Ewan, Bertrand, and Vanessa. So if I say anything right, it's due to them. If I say anything wrong, it's my fault. So just in case people don't know, Roman is named after Nancy Grace Roman. She was the first female administrator at NASA. She was chief scientist for several decades, and is often considered the mother of Hubble. So we're very lucky to have Roman named after such an important figure in NASA's history. So just for background, most people know this, but what is Roman? It was the #1 recommendation of the Decadal Survey 2010 for a large space mission. It was originally called the Wide Field Infrared Survey Telescope. It was a notional mission based on 3 different input mission designs. One was JDEM Omega, which is a dark energy mission, the microlensing planet finder, which was an exoplanet demographics mission using microlensing, and then the near infrared sky survey, which was, as it says, a near infrared sky survey. And according to the 2010 Decadal Survey, there were 3 equal science areas: a dark energy survey using supernova, weak lensing, and baryon acoustic oscillations, exoplanet microlensing survey, and then a geo program, including a galactic plane survey. So the current design, sorry for that typo, is based on what's called the AFTA W1st study, which was completed several years ago. They studied the application of 2 telescopes, which were donated to NASA by a government agency, which shall not be named. And NASA chose to use one of these for W1st, now Roman. So these were 2.4 meter space qualified telescopes, including mirrored spacecraft assemblies. And because of the larger aperture relative to the previous designs, which were sort of 1.3 to 1.5 meters, it became interesting to consider high contrast imaging using a coronagraph for using these telescopes. So this is the current design of Roman and the final design. It has effective aperture of 2.28 meters, basically the same as Hubble. The field of view is 0.281 square degrees. Wavelengths go from 0.5 to 2 microns. This is for the wide field imager. Basically the diffraction limit is 0.1 arc seconds at 1 micron. Launch is 2026, 5-year prime mission, obviously longer extended mission. Orbit will be at L2. So the wide field, there's 2 instruments: a wide field instrument, which will enable imaging and spectroscopy over thousands of square degrees, or synoptic imaging over smaller areas for doing supernova and microlensing fields. Again, the field of view is 0.281 degrees. That's about 100 times HST. This is done using 18 H4RG detectors. Currently, we have on hand 26 science qualified detectors, so more than enough. And there's 7 filter imaging, including prism and prism spectroscopy. And the Coronagraph is an optical imager. It has polarimetry and spectroscopy capabilities and uses 3 different kinds of Coronagraph masks. The observations are spread between 3 core community surveys: a high latitude wide area survey for things like weak lensing, high latitude time domain survey for things like supernova discovery, and the Galactic bulge time domain survey, which will do, among other things, a microlensing survey for cold exoplanets. And roughly 25 or more % of the time will be devoted to general astrophysics surveys. 3 months of the time will be devoted to Coronagraph technology demonstration observations in the first 18 months of the season. So this is the Coronagraph instrument. This is a technology demonstration instrument. It's not actually required to do science, although the hope is it will do actually very interesting science. This is notably the first space-based Coronagraph with active wavefront control. It has an R50 spectrograph and again can do polarimetry. And the improvement in the contrast ratio is 100 to 1,000 times what's currently available from space or the ground. And so this is sort of the capabilities of the CGI are encapsulated in this figure. It shows the flux ratio to the host star of a point source relative to the separation in arc seconds. These contrast curves or contrast curves, rough estimates for ground-based or other space-based platforms. And you can see here their contrasts are sort of 10 to the -5 to 10 to the -7. We've heard a lot about this. These red squares are actually known young directly imaged planets. So this is their contrast ratio in the infrared, 1.6 microns. And then connected to them is the diamonds, the predicted contrast ratio in the optical. And in general, these have not been observed from the ground in the optical because of the difficulties of doing AO in the optical. This shows the predicted contrast curves for Roman CGI in either imaging with the hybrid Leo Coronagraph or in the shaped pupil spectrograph or spectroscopy in the shaped pupil spectrograph. So you can see the improvement of 100 to 1,000 depending on the separation. And these gray triangles are actually known Jupiters around nearby stars, the predicted reflected light signature of those. And you can see that they are just popping up above the, some of them are just popping up above these contrast curves. So Roman CGI will be able to detect and take spectra of a handful of mature Jupiters around the nearest stars. In terms of debris disks, it is capable of imaging debris disks, all of the known debris disks, which are of course above the known contrast curves, and obviously debris disks which are fainter than that. It will also be sensitive to exozodies if they're substantial. So this is a sort of the rough contrast limit as a function of separation for a zodi that's 15 times more massive than ours. And again, you can see it just peaks up above this curve. Okay, so these are the 3 bands I just mentioned: a narrow field of view with a shaped pupil, or sorry, the hybrid Leo, wide with a shaped pupil, and then the spectroscopy with a shaped pupil. There are other masks and filters, but they aren't not required to be fully ground tested, so they can't be guaranteed to work. I'm going to actually just very quickly, and there's lots more of this in my pre-recorded talk. We can really get the first spectra of mature hot Jupiters with the CGI, which will allow us to do things like constrain the metallices of these systems. And some of this will be done in the technology demonstration phase, but obviously there's opportunities for guest observer science later on in the mission. Again, we could do debris disks. The known debris disks are relatively easy, although many of them don't quite fit in the field of view. The challenge here is that they're resolved, so you have to be careful to not remove them in post-processing. But these are things that have been studied, and we know how to deal with them. And again, not only can we learn about exozodi to learn about planet formation, as we heard from Mark Wyatt's talk, but it's also important to characterize the level of exozodies, because this is going to provide a noise background for direct imaging search for Earth-like planets, which Aki will talk about after me.
So Scott, you have 5 minutes to go.
All right, I'm going to go right through the exoplanet demographics. So the other instrument is the wide field imager. Again, 18 H4RGs, 300 megapixels. You can see the filter curves here. So it has filters all the way from the sort of 0.5 to 2 microns. There's a wide filter that goes from 1 to 2 microns roughly. That's the one that the bulge variability survey is going to be taken in. And this is a really pretty picture of 18 detectors in a engineering test unit, just to show that this is a real thing. Just, I forgot to mention, Roman's in phase C, which means it's in the final design and fabrication phase. It's a very much a real mission. It has been supported in the last budget by the president and the House. So this is very much a real mission. The bulge variability survey, one of the goals is to do a microlensing survey of cold exoplanets. So this is the notional survey properties. So 7 fields of a total 7 square degrees, 15-minute cadence, 50-second exposures. There'll be observations and other filters to get color information on a lower cadence. It's going to be 6 72-day seasons for a total of 41,000 exposures in the wide filter, spread over 432 days of our 5-year mission. And again, this is notional. The final survey design will be finalized closer to launch with extensive input from the community. And this is, I don't have time to go into how microlensing works or how it can be used to characterize cold exoplanets. That's all in the pre-recorded talk. Just to summarize what we expect from this survey, about 1,400 bound planet detections, so a large sample, not quite as large as Kepler, but still large, and probably the second largest statistical sample of exoplanets after Kepler. We'll have some sensitivity to outer habitable zone planets, so we can use that to extrapolate into the habitable zone and get a better estimate of Eta Earth. We'll be sensitive to analogs of all the solar systems except for Mercury. So this actually goes to addressing one of Chaz's questions, which is how common are solar systems, and can we put our solar system in the context of other planetary systems? We'll detect hundreds of free-floating planets, including many dozens with mass less than that of the Earth. We'll be able to characterize the majority of host stars, which means we'll be able to get the masses and mass of the host stars and the planets and the distances to the host stars. So we can measure the galactic distribution of planets, frequency of planets in the disk versus bulge, for example. We'll be sensitive even to lunar mass satellites. So Earth-Moon analogs, we'll be able to detect those. As a byproduct, we'll detect about 100,000 transiting planets. So I don't have time to go into the details. Just because of the sheer number of data points, the wide filter, the relatively large aperture, we're going to get an enormous number of photons for a typical star of about 21st magnitude. So per exposure, we'll get about 1% photometry, 1 milliarc second astrometry. And of course, if we can harness all of the statistical power of the 41,000 observations, we can beat all of those down by a factor of 200. So we're starting to get into microarc second astrometry if we can control systematics. And that's a big if, of course. And we're going to be doing this for hundreds of millions of stars. So this is rough estimate of the number of stars as a function of the magnitude. So down to 21st, we're talking about hundreds of millions of stars. We're talking about tens of thousands of microlensing events. And just as one example of what you can do with that, this is the 100,000, this is an exploration of the number of transiting planets we expect to find in the sample. This is originally estimated by Bennett and Reed in 2002, but explored more thoroughly by Ben Monte and collaborators a couple years back. And this just shows the number of expected detections as a function of the radius of the transiting planet for different spectral types. And so for solar type stars, we expect up to 60 transiting Neptunes or super Earths, and 70,000 transiting planets in total. And when we get down to M dwarf primaries, we expect sort of hundreds of 2 to 4 Earth radii planets, and hundreds of giant planets as well. This is the intrinsic frequency of giant planets around M dwarfs. Short period giant planets around M dwarfs is relatively small. And because of the very long time baseline, it's actually possible to get single transit events of planets all the way with periods all the way out to 30 years. Now, what you could do with all of these transiting planets remains a topic that needs to be explored in more detail. It was explored preliminarily in this paper here, but it's going to have to be a pretty heavy statistical analysis to rule out false positives or to statistically exclude false positives. And so with that, I just want to mention that Roman is, it's an unusual flagship mission in that it's largely survey based, but the survey designs are not set There have been notional explorations of them, as I mentioned, but the survey designs are not set. And there's lots of opportunities for the community to get involved to help define these surveys, figure out how to extract science from them. So stay tuned, look for these upcoming opportunities, because this is very much a flagship mission for the whole community, not just for the people that have been working on it for the last 10 years. So I encourage everyone to think pretty hard about what you can do with these kinds of surveys, because we've only scratched the surface of the power of both the CGI and the WFI for exciting science. Thanks.
Great. Thank you, Scott.
Sorry, a little bit over.
Yeah, no problem. We'll take it out of you some other way later.
I have no doubt.
So we move now from things that are, fully funded and are sort of slightly more notional. We're all waiting for the report from the Astro 2020 Decadal Committee to tell us about what future flagship missions might be to explore exoplanets from space. We have a lot of expectations that a major flagship could actually take us all the way to finding a habitable Earth and maybe even an inhabited planet. And Aki Roberts has been heavily involved in the development of the various concepts. So Aki, take it away. We'll have 12 minutes.
Okay, thanks. So first of all, are you seeing my slide?
Yes.
Okay. All right, so I'm Aki Roberts. I'm an astrophysicist at NASA's Goddard Space Flight Center. And I'm going to apologize in advance. I've gotten my kids nasty cold, so pre-apologizing for sniffles and coughs. Okay, so for this summary, I've moved some slides from the full recorded talk into backup. But if you have any questions about the longer talk, I hope we can get to those too. Okay, so in January 2016, NASA started 4 studies of large astrophysics space observatory concepts in preparation for the Astro 2020 Decadal Survey. So the 4 in alphabetical order are the Habitable Exoplanet Observatory, HABEX, the Large UV Optical Infrared Surveyor, LUVOIR, the LYNX X-ray Observatory, and the Origin Space Telescope. Okay, so what's the difference between these missions? And we'll start with wavelength, of course. So at the top, I've placed the wavelength ranges of some past, current, and upcoming large missions. So LYNX is an X-ray telescope, primarily aimed at studies of high energy phenomena. So it can do highly valuable science on young stellar objects and stellar activity, but its exoplanet and disk applications are somewhat limited. So I was not asked to discuss LYNX for this workshop, and I'm not going to say anything more about it. Next up is HABEX and LUVOIR. These missions span a similar UV optical near-infrared bandpass, much like the Hubble Space Telescope, which is happily back to operations now. And finally, we have Origins, which spans a very broad bandpass from the near-infrared to the far infrared. Okay, so I'll start with LUVOIR and HABEX. And I've chosen to discuss these concepts together, LUVEX, as it were. Besides the similar wavelength range of these 2 missions, they have similar driving science goals, differing largely in the quantitative levels of ambition. And reflecting that, the instruments studied for the 2 missions are also similar in many ways. Since I'm most familiar with LUVOIR, because I was the study scientist for that mission concept, I'm going to kick off with that. But as I go, I'll try to point out a few ways in which LUVOIR and HABEX are alike and how they differ. Okay, so here's a high-level overview of LUVOIR, which is a concept for a powerful and flexible space telescope with very broad science capabilities. So the LUVOIR team studied 2 distinct observatory designs. LUVOIR B at the bottom has a large 8-meter diameter primary mirror, and LUVOIR A at the top has a really large 15-meter diameter mirror. 4 candidate science instruments were studied, which provide imaging and spectroscopy over a total wavelength range from the far UV to the near infrared. And there's more about the instruments in the recorded talk. So all 4 large mission studies assumed that mission development starts in 2025. Given that, we would expect LUVOIR to launch in the late 2030s. And we envision it as a serviceable and upgradable facility lasting for decades, with capabilities and operations that are driven by evolving needs, much like Hubble. Okay, so I'll now briefly go over the design features of HABEX. So most importantly, it has a 4-meter diameter unobscured primary mirror. The total wavelength range is a little smaller than that of LUVOIR, but it basically covers the same bandpass. The team studied 4 instruments as well, 3 of which are quite similar to LUVOIR instruments. But there is a key difference between LUVOIR HABEX, and which is that HABEX incorporates 2 different starlight suppression systems for high contrast observations of exoplanets. So in addition to a coronagraph like LUVOIR, HABEX also has a free-flying star shade that is external to the observatory. And I would love to say more about star shades, but I don't have time. It's in the recorded talk. So with the same 2025 start date as LUVOIR, the expected launch date for HABEX is in the mid-2030s. Okay, so now I'll turn to the science of LUVOIR and HABEX. They both will enable an enormous range of science investigations, spanning all the topics covered with Hubble and more. And I'll just go over the mission's key science cases relating to planet formation and evolution. In the full version of this talk, I briefly discussed the mission's driving goal of finding habitable exoplanet candidates and searching them for signs of life. Here, I'll just hit a couple of high points and then jump to the bottom line. Okay, so LUVEX will find those habitable planet candidates in high contrast direct imaging data like this. Such images will be obtained for hundreds of nearby well-known stars with LUVOIR and dozens with HABEX. The stars are mostly solar type FGK stars with some low mass M dwarfs and a few high mass A stars. And here's the bottom line. This plot shows the estimated yields of different kinds of exoplanets discovered with LUVOIR A and LUVOIR B during the Habitable Planet Survey. These range from rocky planets, both smaller and larger than Earth, to gas-rich subneptunes, to Neptune and Jupiter-sized giant planets. And here are the expected yields for HABEX. So in total, LUVOIR A and B will find several hundred other kinds of exoplanets during the Habitable Planet Survey, while HABEX will find nearly 200. And the key point is that these planets will inevitably have a range of ages, providing the opportunity to examine the evolution of planetary atmospheres in a statistically robust fashion. And a very diverse set of observations will be possible for this huge range of planets, which will vastly expand our fundamental understanding of planetary processes across a very wide range of parameters. So first of all, cold to warm planets can be probed at near UV to near infrared wavelengths with high quality, high contrast, direct spectra. So these simulated reflectance spectra were calculated for LUVOIR, but similar observations are possible with HABEX. So the missions can probe the atmospheres of warm to hot exoplanets with transmission spectroscopy from the optical to the near infrared. And the quality of the spectra will far surpass that of current HST transit spectra. And then finally, LUVEX transit spectroscopy in the far UV will have the unique ability to measure atmospheric escape rates for very hot evaporating exoplanets. And this will help to connect the observed atmospheres of mature giant planets to their initial composition at formation. Okay, so now moving back in time to the formation phases of planetary systems. The history of a system is encoded in its arrangement of planets and planetesimal belts, the system architecture. So in the recorded talk, you can see more about what LUVEX can do for debris disks. Here, I'm just going to talk about one key piece of the dynamical history puzzle, which is orbits and masses for all the planets in the system. LUVEX multi-epoch direct imaging will provide orbits for all the planets observed. Then for the masses, for larger planets, their minimum masses can be measured with ground-based radial velocity observations. And then LUVEX will measure the planet's orbital inclinations and provide the actual masses. To ensure measurement of masses for terrestrial planets and for all planets in more face-on systems, the LUVOIR team included an onboard high-precision astrometry mode. And while this feature may not be feasible for HABEX, it is possible that ground-based RV using the future extremely large telescopes, which I think we'll hear about next, will provide masses down to Earth mass around sun-like stars. So in sum, LUVOIR can provide powerful information on planetary system architectures that's needed for high fidelity dynamical modeling. And HABEX can do the same with some help from the future ELTs. Okay, so now we turn to the even earlier phases of planet formation. So the bulk of the mass in a protoplanetary disk is molecular hydrogen. The infrared transitions of H2 are very weak, and this molecule is notoriously hard to observe in emission. Some people call it the dark matter of planet formation. However, the far UV transitions of H2 are very strong. So absorption spectroscopy at far UV wavelengths can sensitively measure H2 at a wide range of temperatures. And in addition, many strong lines of other important molecules lie in the far UV, including water, which is, as you know, hard to observe from the ground. So instruments on LUVEX can obtain these important protoplanetary disk spectra with the primary goal of directly tracing the dissipation of primordial disk material and better establishing the timescales for planet formation as functions of distance from the star. And most importantly, these instruments were designed to do it efficiently via multi-object spectroscopy. So a single LUVEX map of a dense area like the Orion Nebula cluster provides a larger and higher quality data set than the entire medium resolution UV spectroscopic archive of protoplanetary disks from 3 decades of HST observations. And then finally, another important science case for LUVEX is observing the accretion of young protoplanets embedded in protoplanetary disks. So this accretion produces shocked hydrogen emission in the optical H-alpha line and excess continuum emission at UV wavelengths, as seen in these images from Hubble. So while the H-alpha line is accessible from the ground, the UV continuum emission is actually better for measuring mass accretion rates. And so that makes it a valuable complement to ground-based observations. So in sum, I would say both LUVOIR and HABEX can make transformative contributions to our understanding of exoplanets, planet evolution, and planet formation. Okay, now for the ORIGINS mission concept. So ORIGINS has a 5.9 meter primary mirror, and the observatory spans a very broad bandpass from the near to the far infrared. The key feature enabling the long wavelengths is the very cold telescope temperature, 4.5 kelvins, compared to JWST's 50 Kelvin temperature. The overall mission architecture is far more similar to that of Spitzer than it is to JWST. It has a barrel and a cylindrical 2-layer sunshield. And like HABEX, the expected launch date would be in the mid-2030s. So a key goal for ORIGINS is to follow the trail of water from protostars to protoplanetary and debris disks and into our own solar system. And the observatory would have access to many lines of water vapor across a wide range of temperatures, as you can see in this plot here. So observations of emission from water at different temperatures combined with advanced disk models will allow pictures of the disk temperature structure and water distribution to be constructed. And thus ORIGINS would provide sensitive measurements of water in about 1,000 protoplanetary disks, enabling an enormous advance of how water and other volatiles are incorporated into planets. Okay, now moving into the late stages of terrestrial planet formation, debris disks contain small amounts of gas as well as dust. And like the dust, the gas comes from destruction of young planetesimals, but unfortunately it is far less well studied. For a small handful of debris disks, the Herschel Space Observatory detected neutral oxygen and first ionized carbon emission. And those same emission lines are accessible with ORIGINS at much higher sensitivity. Thus, ORIGINS can provide the missing pieces to enable measurements of C/O ratios in about 100 debris disks. And that's a key abundance ratio that hopefully will permit inferences about the abundance of water and other volatiles that are actually in the parent bodies. Okay, and on
About
that
2
note,
minutes, Aki.
okay, getting close. The question of what bodies delivered that water, deliver the water that makes up Earth's oceans has been plaguing scientists for quite some time. So the deuterium to hydrogen ratio in Earth's ocean water is marked with the horizontal line. And this has been interpreted as a sign that outer belt asteroids were the primary source rather than comets, which tend to have higher ratios. However, there are very few measurements of DDH ratios in asteroids and comets, and considerable scatter within those measurements. So via observations of H2O and HDO emission lines, Origins can measure the DDH ratios in more than 100 solar system comets. And this will greatly improve our knowledge of the DDH abundance pattern in solar system planetesimals. It'll provide more precise information on the formation locations of those planetesimals, and hopefully reveal which specific population or mix of populations deliver to Earth's water. So that's it. I've briefly gone over some of the exciting science drivers for LUVOIR, HabEx, and Origins. And these represent, in my view, truly transformative science that would change the whole field of astronomy, just as an earlier generation of great observatories did. But powerful, general purpose observatories like these would have the ability to do science investigations that we haven't even dreamt of yet. And for me, that is perhaps the most exciting thing about them. That's it.
Okay, great. Aki, thanks so much. And we have one last talk where we'll hear about what the future is for ground-based telescopes, both in Europe and in the US. And Marcus Kasper, who's working on the European project to build a ELT, will give us an idea of what those can do for exoplanet science. And then at the end of Marcus, your talk, I'll give you 12 minutes. We'll have some time to compare and contrast everything that we've heard about and answer some questions. Marcus, take it away.
Okay, thank you very much. So my name is Marcus Kasper. I'm working at the European Southern Observatory in Munich in Germany. And normally I work on high contrast imaging instrumentation, but today I'll talk a bit about the power of big telescopes. And on this plot here on the right side, you see the evolution of telescope aperture area over time since the invention of the telescope about 400 years ago. And what you can see is that during this 400 years, the telescope apertures have increased in size by about a factor of 1 million. And we are now currently in the process of building the extremely large telescopes that you see here in the upper right, which are the European ELT, so and the two American projects, which are the 30-meter telescope in the GMT. So this increase in telescope size certainly has a reason, and these reasons are summarized here on the left side. So first of all, bigger telescopes increase the spatial resolution power of the telescope. So this is just going with 1 over the aperture diameter. Then you collect obviously more light with bigger telescopes. So that goes with the aperture area, so d squared. And the speed to reach a certain SNR observation goes even with the 4th power of the telescope diameter. And there's a slide later where I explain why this is the case. So on this here is a simulation of an observation of an object. So this is, I believe, NGC 3603. So there's a cluster of massive stars in the center, and you can see that with a relatively small telescope, you see a single blob of light. And as you go on to bigger and bigger apertures, you start to resolve this in hundreds of stars. And you also see that the sensitivity goes up, so you see more fainter small dots. So there's a resolution and sensitivity, again, nicely illustrated by this figure here. But one has to stress a point that if you observe from the ground, you definitely need a technology that's called adaptive optics to recover the diffraction and limited resolution capabilities. So here's this slide that motivates a bit, or the reasoning for these scaling laws that I've mentioned before. So yeah, the big telescopes collect flux proportional to their aperture area, so it goes with d square. And then if you consider a diffraction limited point source, then the flux is also on top of that concentrated into a smaller patch on the sky. So the diffraction limit shrinks and the area shrinks with 1 over d square. At the same time, the sky noise stays constant. And that is because the flux is increased, yes, of a patch of this noise. But at the same time, the patch size decreases. So and these two effects compensate each other. So the signal to noise ratio is proportional to d square. So signal goes with d square, noise stays constant. And also you gain, when you observe longer, you gain with the square root of exposure time, simply because you collect more photons. And so if you then use this formula, you turn it around, you can see that the time to reach a certain signal-to-noise ratio goes with 1 over the fourth power of the telescope diameter. So that's a very impressive advantage that you have with big telescopes. So when you compare a 40 meter to an 8 meter telescope, so there's a factor of 5 in the aperture diameter, then the speed of the telescope from 8 to 40 increases by 5 to the power of 4. And so that means it's 625 faster. So a 40 meter telescope can do in 1 minute what the 8 meter telescope can do in 10 hours of observation. At the same time, also the magnitude limit increases, this times by 5 squared. So this would be a factor 25. And just to give you the idea, so typically with an 8 meter telescope, you are in the infrared, you have a sensitivity of about a magnitude of 23. So that will increase with a 40 meter telescope to about 26.5. So here's a slide showing how a big telescope, in this case, the European ELT, how it will look like. So current 8 meter telescopes typically have 3 mirrors. So you have a main mirror, you have the secondary mirror, and then you have possibly a tertiary mirror, which just reflects the light off to the Nasmyth platform. So this third mirror here is, in the case of the ELT, replaced by a huge structure. So there's a large tower which contains another 3 mirrors. So the light bounces back and forth in this central area. And the main reason is that this gives us the possibility to include also adaptive optics mirrors into the telescope design. So there is an adaptive M4 mirror here. And then there is also a mirror called M5, which is able to apply a tip tilt correction and correct for wind shake of the telescope and also the tip tilt of the atmosphere. And then the light is directed out to the Nasmyth platform that you can see on the left or the right here. So this big structure, for comparison, you see people down here. This of course also tilts with the telescope, so it gives you an idea. If you tilt this by 70 degrees, then of course you have very tight constraints on flexures. So it is a challenging engineering problem to build this thing on the whole telescope as such. So just a few more details on one of these mirrors. Since I'm working on adaptive optics, I'm most excited about the M4 mirror. So this is an adaptive mirror. It's built by a consortium, Adoptica in Italy, and the shells, so the optical surface, is built by a company called Safran Reosque in France. So this mirror has 5,350 actuators. So these are voice coil actuators, and you see here the reference body of the mirror, and it has 5,000 holes where the voice coils go through, and they connect to the shell that you see here in the process of being polished. After the polishing process, this shell will be just 2 millimeters thick. So it's a very fragile thing. And there will be 6 of those connected to the reference body. And together they act as the deformable M4 with 2.4 meters diameter. Another important asset of the telescope will be several so-called laser guide stars. So adaptive optics, you may know that for adaptive optics, you need a bright guide star that is reasonably close to the astronomical target that you want to observe. So that is very often not the case. So the sky coverage with just using natural guide stars is only a few percent. And you can overcome this limitation by creating your own star in the atmosphere. And you do that by shining light of the appropriate wavelengths into the atmosphere. And then at 90 kilometer height, there happens to be a layer of sodium atoms. And these sodium atoms absorb the light and re-emit it. And so you create a patch of light at 90 kilometers. And so you can use this for adaptive optics. So this laser guide star adaptive optics is also established technology. You see here an actual picture of the VLT, which has 4 such lasers, and the ELT will have either 6 or 8 such lasers. Another important thing is that big telescopes will need big instruments, and the reason is this simple formula here. The size of in the image plane, the physical size in the image plane is a focal length times the angular size on the sky. So a big telescope has a longer focal length, roughly is proportional to the telescope diameter. And so that means that a certain patch on the sky is much bigger for the ELT than it is for a smaller telescope. You can see here, for example, Jupiter is 13 centimeters across in the focus of the ELT. Of course, this results in big focal planes that you need big optics to relay these big focal planes, and this over as a summary effect will just simply increase the telescope as an instrument size proportional to the telescope size. You can see that here nicely illustrated on the Nasmyth platform of the ELT. So this Nasmyth platform has approximately the size of two tennis courts next to each other. And here are the first generation instruments for the ELT. It's an IFS called HARMONI. There's a near-infrared camera spectrograph called Mikado, and there's a mid-infrared instrument called METIS, and also a big structure which hosts a multi-conjugate adaptive optics system, and it's called Maori. So you can see here the people in comparison are relatively small. The instruments are huge. And all this should be realized like that with first light on the time frame 2027 to 2028. So the ELT will, of course, also do great things for high contrast imaging. The first generation, I have now 3 slides that show illustrate a bit the capabilities of these first generation instruments. So Mikado, for example, with just simple classical ADI has already the contrast at larger angular separation that sphere with a PCA reconstruction provides. So we are talking here about a few times 10 to the -6 at a few tens of milli-arc seconds, arc second separation, sorry. But the big advantage of the ELT is, of course, that you can get much smaller inner working angles. So with Mikado, you will be able to observe at an inner working angle of about 30 milli-arc second. And if you translate this into the Taurus star forming region, that means that you can resolve planets that are orbiting at about 4 AU, so relatively close to the ice line of forming stars. So these are 2 different wavelengths. So this K-band on the right side, H-band on the left side, not much different here. And you can also see a few planet models injected here. So the young planets with a temperature of about 1000 Kelvin or so can be observed. The next instrument I want to mention is HARMONI. So HARMONI has very similar contrast as Mikado. We are again talking about 10 to the -6. So you see here the contrast curve. There are simulations here, in this case, of young stars, 20 megayear-old at a separation of at a distance of 30 parsec. And you can see that at a decent SNR in a reasonable exposure time, you can start to image 3 Jupiter mass planets at 1 AU for such a star. And finally, I want to mention METIS. So METIS is a mid-infrared instrument. Again, contrasts are very similar. So you see here an analysis done considering various error sources. Typical contrasts of the order of 10 to the -6 at 0.2 arc second and going down to 10 to the -7, closer to 0.5 arc second separation. The good thing about the mid-IR is that you can observe colder planets. So this is particularly interesting for the observation of planets that are just heated by the stars and not young. And in this simulation down here, you see a terrestrial planet put around Alpha Centauri A at half an AU and at 1 AU. And at 10 microns, the sensitivity is sufficient to detect both these planets. So the one at 0.5, which is a bit hotter and therefore brighter. And at shorter wavelengths in M-band and L-band, you can still see the warmer one. The one that has more like Earth temperature is too cold and will fade away at these shorter wavelengths. And this plot shows what I just mentioned, the discovery space of METIS. So you see here terrestrial planets in the habitable zone put around nearby stars. So there's one planet per star. And the METIS limitation is also quite obvious here. It's the inner working angle. So at the long wavelengths, even with the ELT, you cannot resolve inside of about 100 milli-arc seconds, so 0.1 arc second. And so that means the number of stars that you can observe is relatively small, as a handful of stars, and they all have very well-known names. And if you really want to get access to the large number of nearby M stars, you have to go to the optical wavelengths. And I just want to mention this because I'm working on that myself. There is a concept, it's not an approved project yet, it's called Planetary Camera and Spectrograph. It's a high contrast imaging instrument dedicated to the characterization of terrestrial planets. And this one will work at the optical short near-infrared wavelength and has as a target the observation of the nearby M stars. And so this brings me to my last slide. It's just a summary slide. Mentioned maybe just the main takeaway message of that is that the ELTs will be really formidable for studying planet formation and also low mass planet characterization. These are the two main things where I'm very excited about and can't wait for these telescopes to come online. And that's it. Thank you.
Okay, Marcus, thank you very much. And thanks to all of our speakers. We don't have a lot of time left for questions, but I'm certainly willing to first ask if any of the panelists would like to ask a question of any of their other fellow panelists. I'd open that up. Aki, you want to pose a question to anybody?
Yeah, I'd like to hear from Marcus about the prospects for future ground-based RV with the ELTs, actually, because kind of important for, as I was talked about mentioned in my talk.
For RV, yes, there is one, I didn't mention this because it's not really the first generation, it's probably the 1.5th generation. There is an instrument concept called HIRIS. So there will be an RV machine for the ELT as well. The project is just about to start. So yes, I mean, the ELT will also do RV observations. That's true. And PCS, by the way, will also most likely have a high resolution spectrograph on top to get the high contrast. So we will combine the extreme adaptive optics with a high dispersion spectroscopy.
There's the GCLEF instrument, which I think is a first generation instrument for the GMT as well.
Yeah. Okay, Scott, pose a question or comment?
So Aki, one of the challenges is with direct imaging experiments is that we can't get the masses. Can you say a little bit about the prospects for getting masses with LUVOIR? It was in your slide, but yeah.
Yeah, I went by that pretty fast. Well, the idea is that we would use LUVOIR's wide field camera, actually, to do, not the Coronagraph, but the wide field instrument, to do ultra high precision astrometry measurements. So looking for not the reflex RV motion of the star, but this one, the other wobble as the as planets orbit the star, like what Gaia is doing, but more precisely. And like I said, if we need it, okay, it looks like we could do it. If we don't need it, if the ELTs can provide, masses of, Earth mass planets around sun-like stars, then fantastic. That would be great, because if you can do it from the ground, you don't do it from space.
Okay, Christine. Anything? Let me pose one question to you, then you get a turn. Everyone wants to know, can you give us an update on status for launch?
Status for launch. So everything is proceeding on schedule. And so the telescope is expected to ship to South America in August. So really what's setting the launch date right now is the Ariane SPA schedule for when the Ariane rocket will be available. So there are 2 launches in front of JWST right now. I believe the first is been rescheduled for about July 30th. And there's about a 60-day turnaround time between launches. So if you work it out, JWST is most likely to launch around November 30th, at the end of November.
Okay, great. Thank you. We're all counting it down with all of you at the Institute and at the project. So anything you'd like to pose to the panelists? Okay, and Marcus, anything you'd like to pose?
No, I'm fine. Thanks.
Okay, I had one question for you. As you noted, the size of these seeing limit instruments, or even diffraction limit instruments, get awfully large. The scaling with diameter is pretty unfavorable. Have you considered at least looking at these diffraction limited fiber-fed spectrometers that are now starting to come online on a couple of telescopes where you're decoupled from the size of the telescope once you get the light into the fiber?
So the first generation instruments actually do not consider this, but as we are a bit behind with PCS, we are looking into this possibility. That's right. And I think for high contrast imaging, it's a very attractive possibility.
Okay. One question for Scott. How do you envision making CGI available to the community as a fully fledged instrument for exoplanet science? Is there anything you see the community doing to help this along with the upcoming proposal activity or whatever?
Good question, Chaz. I think probably you know the answer to this better than I do, but hold on a second. There is a CGI community preparatory or something like that. I'm not that familiar with it. Do you want to say something about it?
The CC CCPP stands for Community Participation Program. Chronograph Community Participation Program. Yeah,
that's it. Thank you.
That's it. Yeah, the idea for that is there will be a call. There'll be a call coming out in the not too distant future in the next year, within the next year, for people to propose themselves to sort of join a team that will work with the CGI project team to prepare for the observations, plan how the tech demo, prepare for the tech demo observations, plan how the tech demo observations will be done, and assess performance on orbit and see whether it is a viable option to be included into the guest observer program, the Roman's guest observer time. I think that's about right, Scott, right?
I think that's about right, yeah.
So one thing that people attending this conference could consider is putting in proposals to be members of that team. So if we had lots and lots of people proposing to participate with CGI, that would indicate an interest. So everybody out there, we have hundreds of people on this workshop, I urge you to propose in the same way that over years I've urged people to propose for JWST, and we now have 25% of the time on JWST going to disks and exoplanets. And as a couple of people have noted in the Slack and so on, this is a remarkably exciting time. It's been an exciting 25 years. The next 25 years will be even more exciting. And I guess I'll close with last question for you all to consider, which is, what would be the most important discovery from the new telescopes, in your opinion? 30 seconds for each of you. Christine.
So as Aki mentioned, oftentimes when you build new instrumentation and launch it, it's hard to really envision what transformational science will happen. And JWST is so capable that we really expect, transformational science across a broad range of science topics. For all those TRAPPIST-1 fans, I'd like to tell you that all 7 planets are going to be observed. And so that'll be an exciting thing to look out for in cycle 1.
Great. Okay. Marcus, most exciting discovery from all the telescopes we've discussed today?
Well, I mean, for me, that's an image of a terrestrial exoplanet in a habitable zone. And well, I mean, I guess the ELT gets probably the first shot at that.
Okay. Scott.
So in terms of Roman specifically, the CGI, there's nothing completely that comes to mind that's going to be a surprise. But again, we're looking at contrast ratios that are 100 to 1,000 times smaller than we've ever been able to look at before. So there very well could be surprises. In terms of the demographics, it's just what everyone has said. We're opening up this enormous new region of parameter space, and we have no idea what we're going to find out there. It could be that there's a whole bunch of failed Jupiters. It could be that there's giant planets. Who knows? And I think and in terms of free-floating planets, again, it's just wide open. The galaxy could be teeming with them, and we wouldn't know, but Roman will tell us.
Okay, and Aki, take us home.
Well, for me, it's fairly predictable, really. What I want to see, most exciting thing is pale blue or orange dot around a nearby sun-like star that actually shows biosignatures, either one similar to what we see in the modern Earth, like oxygen or O2, or ones that like in the Archean Earth, where you'd see methane, CO2. So that's the holy grail, the inhabited Earth-like, but truly Earth-like planet in that it is actually inhabited.
Okay, so for all the people attending the workshop, many of them early career scientists, stick around. The next 25 years promise to be as or more exciting as the previous 25, and we need you all to do the work. And on that, we will close this session and move over to Dawn, who has some concluding remarks.